Hello, our viewers. Previously, we have tried to discuss about linear momentum. We have defined what momentum is. We have said that momentum is a property of massive body to exert force on any obstacles along its motion. We have mathematically expressed momentum as mass times velocity v. Since velocity is a vector quantity and mass is a scalar quantity, momentum is also a vector quantity. The product of scalar and vector gives us vector. Momentum has a unit kilogram meter per second, or it can be equivalently expressed as Newton second. We have also tried to solve a good example. And today we'll proceed from that, and we'll try to see the different types of impacts of linear momentum and the type of momentum. So let's proceed. Linear momentum has many impacts or applications. Among the applications of momentum, the most common is collision. The collision between objects can be expressed using the concept of momentum. The other concept is rocket propulsion. It's also possible to consider recoil, or explosion of things can be expressed using momentum. One good application of momentum is collision. Collision is the impact between two or more objects, and then it has different types of collision. We should have to have criteria to classify collision. The first thing, depending on the lines of the action where those bodies are colliding, it's possible to classify momentum or collision into two: the glancing collision and the head-on collision. Glancing collision has two differently lines of action before and after collision. Suppose here you have two objects. Let's say that this is object 1 is moving in this direction, and we have another object moving in this direction. This is their lines of action before collision. So after they collide together, as these objects collide all together, their lines of action will be changed. For example, if these two bodies are colliding after collision, this object might tend to move in this direction and the other object might move in this direction. So their lines of action differs. For example, here you have a cue ball, so that's moving in this direction and collides with this object. So the lines of action is not on this way. It changes its direction on the other way, and this object was having this it was at rest, it might move on this direction. Such type of collision is known to be glancing collision, depending on the lines of action. The other type of collision, and the most common type of collision, is known to be head-on collision. Head-on collision is a collision in which the lines of action remains constant before and after collision. Suppose you have two objects or two mass, they are moving with different speed oppositely and collides together. After the collision, these objects might move on the same lines of action. These objects might move on this and oppositely, or they might stick together and move together on one direction, or they might move together on the other direction. So the lines of action remains. If the lines of action remains before and after collision, such type of collision is known to be head-on collision. So this is one of the impacts. We mainly focus on the collision, and we'll try to see about the law of conservation of momentum. The law of conservation of momentum is a very important law of the universe. Among the governing rules in the universe, the law of conservation of mass, the law of conservation of energy. Here we have also the law of conservation of momentum. And the law of conservation of momentum is stated that for a given two different isolated objects, mainly focus only for two objects, for a given isolated system, the net force on those bodies is 0, then the momentum is conserved. Previously, we have stated that the net force or the impulse is equals to force times change in t. Force times change in t. The change of momentum means the final momentum minus the initial momentum is known to be impulse. If the net force exerted on those objects is 0, so that J or impulse is 0. If impulse is 0, meaning the final momentum minus the initial momentum is 0. The difference between the final and initial is 0. So if we transfer this, this tells you that the initial momentum is the same as or equals to that of the final momentum. This is known to be the law of conservation of momentum. So for a law of conservation of momentum on a given isolated object, if the net force exerted on them is 0, so that the momentum is conserved. Keep this in your mind. The final and the initial momentum are conserved. It can be restated that the sum of momenta, momentum of different objects, the plural word of momentum, the sum of momenta of two bodies before collision is equals to the sum of momentum or momenta after collision. Let's take two bodies. Here we have mass 1 and mass 2. Mass 1 has initial velocity u1. Let's say that it's moving with its initial velocity u1. And this object is moving with its initial velocity u2, with a constant velocity. So they are moving and colliding together. Okay? After collision, let's say that mass 1 is moving in this direction with a final velocity. After the collision, the velocity might be changed so that we can have v1. And this object has a velocity of v2, okay, v2. So the momentum before collision, the summation of momentum before collision, meaning the momentum of mass 1, the initial momentum of mass 1 can be expressed as mass 1 u1. This is the initial momentum of mass 1, okay? The initial momentum of mass 2, meaning the momentum before collision, is m2 times its initial velocity u2. After collision, these bodies have their own respective velocity, so that they have their own final velocity. The momentum of particle 1, final or after collision, let's say that after collision, is mass 1 times the final velocity. Let's use u as initial velocity, v as final velocity. Before in kinematics, we use the initial velocity as velocity initial and velocity final, like this. But now, the initial velocity is expressed as u, the final velocity can be expressed using v. Therefore, m1 v1 means the collision of particle 1 or mass 1 after collision, and the final velocity of particle 2 or mass 2 is m2 v2. Now, the law of conservation states that the summation of the momentum before collision, the summation of mass 1 and the summation of momentum of mass 2 is equals to the final momentum, the summation of final momentum or the summation of momentum after collision, which is mass 1 v1 and mass 2 v2. So this rule states that m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. This is known to be the law of conservation of momentum. The law of conservation of momentum, and it's very practicable law. Here we have three types of collision. We may say three types of collision depending on the law of conservation of energy. The first type is known to be elastic collision. Under elastic collision, both the momentum and the kinetic energy remains constant. For two objects to collide, they must be in a state of motion so that they do have velocity. If they have velocity, they do have kinetic energy. So the collision before and after collision, they do have the same momentum and the same kinetic energy. And the other type of collision is inelastic collision. For inelastic collision, the momentum remains constant before and after collision, but the kinetic energy differs before and after collision. The kinetic energy after collision is less than the summation of the kinetic energy before collision. So we'll try to see each by one. First, let's try to see about elastic collision. It is one type of collision in which both the momentum and the kinetic energy are conserved. Both the momentum and the kinetic energy conserved. Recall that the law of conservation of energy states that energy is neither created nor destroyed. the total energy of any system in the universe remains constant. But here we are specifically focused on the energy due to the motion of the particles, and that is kinetic energy. So the particles have the same kinetic energy before and after collision. Before and after collision. So the kinetic energy of the particle, suppose here you have a particle, and that particle is moving with an initial velocity u1. As we have previously said, we have u1, and let's say that this is mass 1. We have another mass, let's say that this is mass 2, and mass 2 is moving with an initial velocity u2. So since they have velocity, we can find their kinetic energy. How? We know that kinetic energy is given to be 1 over 2 m1 u1 squared. You have learned this in your lower grades concept, and we'll try to see this under Unit 5 work energy and power concept. Anyways, kinetic energy generally expressed as 1 over 2 times m times velocity squared. This velocity, if it is initial velocity, you might use u. Final, if it is final, you might use v. Anyways, so this is the kinetic energy 1 over 2 m1 u1 squared. This is the initial velocity of particle 1. 1 over 2 m2 u2 squared is the initial kinetic energy of mass 2. After they collide together, and if the collision is elastic collision, those particles are moving. Let's say that it's head-on collision, and their final velocity b v2, and the velocity, the final velocity of mass 1 b v1. If so, substituting here, we can have 1 over 2 m1 v1 squared plus 1 over 2 m2 v2 squared. This is the kinetic energy final or after collision of particle 1, and this is the kinetic energy of particle 2 after collision. So the summation of kinetic energy before collision is always remains the same as that of the summation of kinetic energy after collision for elastic collision. For elastic collision should be elastic collision. And the other concept is the momentum remains constant. Actually, the momentum remains constant for different types of collision, for elastic, inelastic, as well as for recoil or for superelastic collision. We can consider it to be conserved. The momentum remains conserved. So for these two particles, the momentum can be written as m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. This is the momentum. So in this case, we have found the kinetic energy remains constant. As well here, we have found the momentum remains constant. Both the momentum and the kinetic energy are conserved for collisions, elastic collision, for type of collision having elastic collision. So equating these two, we can produce a very fundamental equation used to determine the final velocity of particles. For example, here after collision, if these two bodies has elastic collision, the final velocity of the particles can be given as twice of mass 2 u2, the initial velocity of particle 2, plus mass 1 minus mass 2 times u1 over mass 1 plus mass 2. This is how we determine the final velocity of a particle after collision elastically. If they are collided elastically, it's possible to find the final velocity of particle 1, and the final velocity of particle 2 can be determined using twice of m1 u1 plus m2 minus m1 u2. This is how we determine the final velocity of two particles colliding elastically. How about if two bodies are collide inelastic? Inelastic. The two bodies, after the two bodies are colliding together inelastically, it means that the momentum remains constant, but the kinetic energy differs. The kinetic energy after collision, is less than, after collision is less than the kinetic energy before collision. So when two bodies are collided inelastically, or if the collision is inelastic collision, the kinetic energy does not remain constant. There is no conservation of kinetic energy. That means that when the two bodies are colliding together, their summation of kinetic energy is converted into some other forms of energy. The energy remains constant, the total energy, but the kinetic energy is not conserved, because Let's say when two balls are collide together, they will form sound. Sound is the other form of energy. That kinetic energy might be reduced by some amount. So after collision, they do have a less amount of kinetic energy. Such type of collision is known to be inelastic collision. Inelastic collision. The most common inelastic collision is perfectly inelastic collision. Okay? Perfectly inelastic collision is a type of collision in which the two bodies stick together after collision. Let's say that particle 1 is moving to the right with u1 and particle 2 is moving to the left with u2. As these two bodies are colliding together, let's assume that they are stick together or they embedded together. If so, the two bodies stuck and move in one direction, might be in this direction or in this direction. So the common velocity, this velocity is known to be common velocity. Common velocity can be determined using the law of conservation of mass. Either elastic collision or inelastic collision, we do have a law of conservation of mass. And the law of conservation of momentum states that m1 u1 plus m2 u2 is equals to m1 v1 plus m2 v2. After collision, the final velocity of particle 1 and the final velocity of particle 2 is v, and it's known to be common velocity since they are stuck or embedded together. So keeping this in your mind, m1 u1 plus m2 u2 is equals to the summation of this mass plus mass 1 plus mass 2 as a common, they have this common velocity v. So the common velocity can be determined m1 u1 plus m2 u2 over the summation of total mass m1 plus m2. This is what we call a common velocity. Now let's try to solve one good example. Here we have 2 kilogram block is moving along the positive x-axis with 3 meters per second, and another block which is 4 kilogram is moving oppositely with 1 meter per second. Now it says compute the velocity or try to find the velocity if the collision between the two blocks is elastic collision, if the collision between the two blocks is perfectly elastic. So how do we determine the respective velocity? For the first case, we have two blocks. Let's say that these are the two blocks. They are colliding along x-axis oppositely. It's moving with a velocity, with as initial velocity u1, you can call it u1 to be 3 meter per second. This is 2 kilogram. Let's say that this is mass 1 and mass 1 is 2 kilogram. So 2 kilogram mass is sliding over a frictionless surface. Let's say that it's moving to the positive x-axis 3 meters per second. And the other block is moving oppositely. It says oppositely here, oppositely. Therefore, the initial velocity of particle 2 should be written if this particle is moving to the positive x direction. If you say that this is 3 meters per second, and since it is vector quantity, you should have to put it like minus, okay? The negative of 1 meter per second. It doesn't say negative 1 here, but it tells you that the particle is moving oppositely. If so, you should have to put this, if this is 3, positive 3, you can put this minus 3. If this is minus 3, if you put this negative 3, you should have to put this as plus 3. Because they are moving oppositely, they do have opposite direction. And this is mass 2, and it has 4 kilogram. Let's assume that the two bodies are colliding together, and they collide elastic collision. They have elastic collision. After collision, they have their own final velocity. The final velocity of particle 2, v2, the final velocity of particle 1, v1. We don't know where the particles are moving, by the way. As they collide together, they might, if it is inelastic, perfectly inelastic collision, they might stick together. If after collision, they might move to this direction altogether or to this direction, we don't know. So you just put like this and try to find the velocity. If the velocities are positive, so that they are moving along the x-axis direction, because you have already mentioned that plus is along the positive x direction, and here you have a negative, okay? Negative means along the negative x direction. So the plus and the minus result of the velocity 1 and velocity 2 tells you where the particles are moving. And to find this for elastic collision, previously we have these equations. This equation says that the final velocity of particle 1 can be given as twice of mass 2 times u2 plus m1 minus m2 u1. So this is what we have. So putting this all together, v1 can be determined as twice of mass 2 u2 plus mass 1 minus mass 2 times u1 over mass 1 plus mass 2. That's all. We should have to substitute all the parameters or the variables that we have. So twice of mass 2 is 4 kilogram, and the initial velocity of particle 2 is negative 1, plus mass 1 is 2 kilogram, minus mass 2 is 4 kilogram. Okay, and the initial velocity u1 is 3 meter per second over mass 1, 2 kilogram I mean, and mass 2 is 4. So 2 plus 4. Here 2 times 4 is 8 minus 8, and here 2 minus 4 is negative 2. Negative 2 times 3 gives you negative 6 over 2 plus 4 is 6. So when you add these two, it gives you negative 14 over 6. When you simplify this, you can have negative 7 over 3 meter per second. You see, this is the final velocity of particle 1, and it tells you it is negative, meaning it opposes its direction. The initial direction of mass 1 was 3 meter per second along the positive x direction. Now after collision it changes its direction and it becomes negative. Negative means it changes its direction. How about velocity v2? How do you determine velocity v2? So from the type of collision, previously you have said that v2 can be determined as twice of m1 u1 plus m2 minus m1 u2. This is how we determine. So putting this, v2 can be determined as twice of m1 u1 plus m2 minus m1 the whole u1, okay, over mass 1 plus mass 2. This is the equation used to determine the final velocity of particles after they elastically collide. So substituting this, twice of mass 1 is 2 kilogram, u1 is 3, plus mass 2 is 4 kilogram minus 2 times the initial velocity of particle 1 is 3. This is 2, so you should have to put minus 1, the negative of 1. Okay, it says minus 1 or negative 1 over mass 1 plus mass 2. Mass 1 plus mass 2 is 2 plus 4. 2 plus 4. So when you try to calculate this, this gives you 12. And 4 minus 2 is negative 2. And here you have negative 1. Negative 1 and 4 minus 2 is 2. 2 times minus 1 minus 2 over 6. When you subtract this, gives you 10 over 6. And when you simplify this, you have 5 over 3 meter per second. Look here, the final velocity of this particle becomes positive, meaning initially it was moving in the negative x direction, but after collision it changes its direction so that it's moving along the positive x direction. This is how we determine if the particles are colliding all together in an elastic collision. And it says a perfectly elastic collision. If the two bodies have a perfectly elastic collision, meaning after collision, if they stick together, how do we determine their common velocity? Well, their common velocity can be determined using the previous equation. We have a common velocity, which says that m1 u1 plus m2 u2 over m1 plus m2. So V, the common velocity of these two particles, m1 is 2 kilogram, m2 is 4 kilogram. The initial velocity is 3 of this particle, and this one is -1. So m1 is 2 kilogram, and it's moving with a velocity 3. m2 is 4 kilogram, but it's moving with -1. -1 over m1 is 2 kilogram plus m2 is 4 kilogram. Now look, after collision, those two particles stick together and move in one direction. To which direction? Is it moving to the right, to the left? We don't know. The mathematical formula tells you to which directions are they moving. How do we determine this? Well, when you're trying to calculate this, it tells you 2 times 3 is 6, okay? 4 minus 1 is -4, over 2 plus 4 is 6. When you subtract this, it gives you positive 2 over 6. When you simplify this, it becomes positive 1 over 3 meters per second. So, to which direction are they moving? It gives us positive, meaning that those particles collide together and move to the right, okay? They have a positive value so that they are moving to the right direction. Okay, this is how we determine for elastic and inelastic collision. And there is also a superelastic or a recoil case. A given object might be exploded, or a given compacted things might be relaxed, so that different mass might be moving in different directions. Such type of collision is said to be superelastic collision. And for some common examples of superelastic and recoil can be a cannonball or a cannon. For example, here you have a cannon, and while the cannonball is exploded and moving in this direction, the gun might be, or the cannon might move in this direction oppositely. This ball, the cannonball, moves in this direction, whereas this one tends to move in the opposite direction. And the other impact that we have previously discussed is we have collision is one of the impact of momentum. Rocket propulsion is the other impact of momentum. For a given rocket to be launched, gradually it loses its mass. As it ejects fuel, gradually it loses its mass and its velocity increases. So you have an equation which says that the final velocity can be determined as the initial velocity v plus the ejected velocity. The ejected velocity means the ejected velocity of the fuel. Okay, the fuel gradually loses its mass. The ejected velocity of the mass, the velocity eject. Okay, ln, mathematical expression, ln means logarithm, m initial over m final. Okay, m initial over m final. Actually, the usual question is what is the final velocity of this particle, or the final velocity of the rocket after it loses half of the mass, might be 1/3 of the mass, and so on. So it's possible to apply this equation to find the final velocity of a given rocket as it's launched and moved in space. Let's try to solve one good example here. Suppose you have a rocket moving in a free space has its initial velocity 3 times 10 to the power of 3 meters per second, okay, relative to the Earth. If its engine is turned on in a space, it's moving with a constant 3 times 10 to the power of 3 meters per second. But suddenly it's turned on its engine. While it turns on, it ejects a huge amount of fuel. Okay, the fuel is ejected oppositely to that of the rocket, with that of 5 times 10 to the power of 3 meters per second. This is the ejected velocity of the fuel from the engine. And this is the initial velocity of the rocket. Now the question says that what is the speed of the rocket related to the Earth once the rocket's mass is reduced half of the initial mass. So the initial mass of the rocket, let it be m initial, but the final mass of the rocket becomes half of the initial mass. It is 1/2 of the initial mass. By now, how do we determine its final velocity? Well, to determine its final velocity, we have already provided this equation. It's a direct substitution. So the initial velocity is given to be 3 times 10 to the power of 3 meters per second, plus the ejected velocity of the fuel, the ejected, is given to be 5 times 10 to the power of 3. Ln is natural logarithm. You know that logarithm x to the base e is known to be ln e, ln x. So this is how we determine m initial over m final. M final is 1/2 or 0.5 of mass of initial. So we can find it to be 6.5, approximately 7 times 10 to the power of 3 meter per second. This is the final velocity of the rocket after it loses half of its mass. It's also possible to find 1/3 of the mass, 1/4 of the mass, and so on. There is a so-called thrust force. It's also possible to find the thrust force, and the thrust force can be given using this equation. So this is all that I've got for today. Next time we'll try to see about work, energy, and power. So goodbye.